Hi everybody. All right, this is going to be our last review video, and in this video we're going to review the applications of integration. And since in the last video we talked about how to evaluate definite integrals, which was fundamental theorem of calculus, we're just in these examples going to set up the definite integral just to save time, so this isn't an hour-long video. Okay, so our first application is whenever you integrate a rate of change. So remember, that is equal to the net or total change, okay? So here are some key points that you want to remember. Net change as an integral. If you integrate s prime of t, which remember the derivative is slope, it is a rate of change, from t sub 1 to t sub 2, that is going to equal the net change, or s of t sub 2 minus s of t sub 1, okay? Now, we can take that concept and apply it to motion. So the next key point is, if an object is traveling in a straight line at velocity v of t, then the net change, which we would call displacement, during or from t sub 1 to t sub 2 is equal to the definite integral. Okay, so anytime you integrate velocity, it's going to tell you the net change in position. All right, now, if you want to know the total distance, though, that's when you have to integrate the absolute value of velocity, okay? So remember, we've talked about these things. And it's not a bad idea when you're thinking about motion to remember PVA, position, velocity, acceleration. If you're finding a derivative, then you're working down, and integration is going to reverse that. So you're going to work back up. Okay, so if you find the derivative of position, you get velocity. If you find the derivative of velocity, you get acceleration. If we're working backwards, if you start with acceleration and you integrate, you get the change in velocity. Okay, if you start with velocity and you integrate, you get the change in position. Okay. All right, so let's look at this example. It says a particle is moving along a straight line with velocity equal to cosine of t meters per second. Find the total displacement and the total distance traveled over the time interval from 0 to 4 pi. Okay, so for part A, to find the displacement, that's just your net change. So we're just going to set up the definite integral from 0 to 4 pi of the velocity, so of cosine of t dt. And then you would just evaluate that definite integral. Okay, for part B, though, to find the total distance, that's when you want to put absolute value around your function. Now, if this is let's say it's a non-calculator problem, on the AP exam, you would have to determine where cosine is equal to 0, and you would have to split this up into the sum of two definite integrals, and then if you get a negative value, which you probably would, for your definite integral, then you would just find the absolute value of that and make it positive and then add them all together. So, all right. Moving on. All right, the next application is called average value, or average or mean value of a function on an interval. And so remember, that is where you put 1 over b minus a in front of the definite integral. Okay. This also leads to what is called the mean value theorem for integrals, which says if f of x is continuous on a closed interval from a to b with average value m, then f of c is equal to m for some c in the interval. So graphically, what we're talking about is, remember, the solution to the definite integral is the area. So let's just say that we have some curve from a to b, some function, we'll call it f of x. And the definite integral is going to represent the area between that curve and the x-axis. So all we're saying is somewhere between a and b, there is a value f of c where f of c, let's say that c is right here maybe, where the area of this rectangle is going to equal the area under the curve. Okay. All right. Here's an example. Let m be the average value of f of x equals 2x squared on the interval 0 to 2. Find a value c such that f of c is equal to m. Okay, so we're going to start by finding the average value. So it's going to be 1 over b minus a, which is 2 minus 0, times the definite integral from 0 to 2 of 2x squared dx. Okay, now this one we're actually going to work out because we're going to need it to be able to answer the second part. Okay, so we're going to end up with 1/2 times, then we're going to find the antiderivative. So we're going to get 2 times x cubed over 3. From 0 to 2, and then we could really cross-reduce with the 2's and just simplify this to x cubed over 3 from 0 to 2. Okay, and then we're going to plug in our upper limit, so 2 cubed is 8, we're going to get 8/3 minus 0, so that's equal to 8/3. Okay, so then we want to find a value c such that f of c is equal to m. So we're going to take our original function, 2x squared, and we're going to set it equal to 8/3. And we're just going to solve it for x. So here I would multiply by 1/2 on each side. And then I would find the square root of each side. Now technically when you find a square root you get a positive and a negative solution, but remember we're only interested in the interval from 0 to 2. So we're really just interested in the positive root. So this will actually end up being 2, because we can find the square root of 4, over the square root of 3. Okay, so this is the value of c for x, where the average value for that average height is equal to the area under the curve. Okay, our next application is finding area between two curves. So remember that here you're just setting up a definite integral, but you always want to set it up as upper minus lower. So to find the area between f of x and g of x, if f of x is greater than or equal to g of x, then the area between the graphs is f of x minus g of x. Okay, so an easy way to remember it is upper minus lower. Okay, let's look at the example. It says, let f of x equal 8x minus 10 and g of x equals x squared minus 4x plus 10. Find the points of intersection of the graphs and draw the region bounded by these two functions. Well, I went ahead and graphed them so that we could get a visual. So 8x minus 10 is the red graph, and x squared minus 4x plus 10 is the blue graph. So we're trying to find the area in between, which basically is right here. Okay, so we need to find our points of intersection. If you're able to use a calculator, you would just do that on the calculator. If you cannot use a calculator, to find your points of intersection, you set the functions equal to each other and solve for x. So here we would be solving a quadratic equation, so we'd want to move everything to one side. So we would want to subtract the 8x So that'll give us minus 12x, because we're subtracting 8x from the negative 4x. And then we would want to add 10 to both sides. All right, let's try factoring. We're looking for factors of 20 that add to negative 12. That would be negative 10 and negative 2. So we get x equals 10 and 2, or basically we can tell that this is at 2 and this is at 10 along our x-axis, okay? And that also gives us the limits of integration. So we're going to integrate from 2 to 10, and then we just have to make sure that we set it up as upper minus lower. So for this region, the linear function, or the red graph, would be our upper function, and then the lower function would be the parabola. So we'd want to set it up as 8x minus 10 minus x squared minus 4x plus 10. Okay, and then of course you would evaluate the definite integral. One other thing I want to point out is make sure you put the second function in parentheses, because you're subtracting and you would have to distribute that negative. Okay, so that's a good reminder of that. Okay, here's another example of finding area between two curves, but the difference with this one is that our functions are in terms of y. So if you notice, they're solved for x in terms of y. So in this case, you want to integrate along the y-axis. So we want our limits of integration to be y values, okay? And I know it's a little bit difficult to tell the points of intersection. Well, this one's pretty easy. It's at negative 6. But this one is actually at 5. And I came up with that, again, by just setting the functions equal to each other, and then solving it for 0. You end up with a quadratic, you factor it, and we get negative 6, positive 5. Okay, so those are going to be our limits of integration. So whenever you're integrating along the y-axis, instead of thinking about it as upper minus lower, you want to think of it as right minus left. Okay. All right. So the function to the right is the linear function. This would be the function to the right. That would be the 3y plus 8. Minus the function to the left. Okay. That's kind of what looks like a sideways parabola. That would be the y squared plus 4y minus 22. And you want to set it up as dy. Okay, you want your differential to be dy because your functions are in terms of y. But this would be your definite integral, and then of course you would just solve it. Okay, from there we moved into volume. So once you can find the area between two curves, one way to find volume is called the disk method. So that essentially is taking that area and rotating it around an axis, okay? So when you rotate it around an axis, the cross section is a circle. So to find the volume, you're just integrating area of a circle, which is pi r squared, okay? So the area of the cross section is a circle. That area is pi r squared. In this case, r is going to equal your function, f of x. So basically, you end up with this definite integral, volume is equal to pi times the integral from a to b of f of x squared dx. Okay? All right. Now, I'm going to jump back to the first one. To find the volume of a solid where you are told what the cross-section looks like. So the cross-section might not be a circle, it might be a square or an equilateral triangle or something other than a circle. that's when you're just going to integrate the area of the cross section. Okay, so remember that A of y in this case is the area of the cross section. Okay. All right, and then the third method is the washer method. This is when you're going to have a gap between the area, the region that you're rotating around the axis, and the axis of revolution. So this is when you're going to have a big r squared and a little r squared. Okay. So your definite integral is pi times the integral from a to b of f of x squared minus g of x squared, where f of x is your big R and g of x is your little r. Okay. All right, let's look at some examples. I think this is one we may have done previously. All right, so here it says let f and g be the functions given by f of x equals 1/4 plus sine of pi times x, and g of x equals 4 to the negative x power. Let R be the shaded region in the first quadrant enclosed by the y-axis and the graphs of f and g. Let S be the shaded region in the first quadrant enclosed by the graphs of f and g as shown in the figure above. Okay, so we want to start by finding the area. Actually, since we've already done some of those examples, we're going to go right to C, and we're going to find the volume of the solid generated when S is revolved about the horizontal line y equals -1. Okay, so we're only dealing with this region here. Okay. And we're going to revolve this around the line y equals -1. That is the axis of revolution. Okay, so you can definitely see there's a gap between the region that we're rotating and the axis of revolution. So this tells me that we have to use the washer method. Okay. All right, so to find your big R, what you're going to do is you're going to connect each function to your axis of revolution. Okay, so I'm going to connect here, here. The longer segment is big R, the smaller segment is little r. Okay, now, to find the function for r, big R, you're still using upper minus lower, okay? So our upper function in this case actually is our sine function. So it's going to be 1/4 plus sine of pi times x minus -1, because that horizontal line at -1 would be like your lower function, okay? And then little r is going to be 4 to the negative x minus -1. Okay, so these will become +1 since we're subtracting a negative. And then we can set up our definite integral. Now, the last thing we need are the points of intersection. And so I actually used the calculator to find these. The x value for this point is 0.17822. And the x coordinate for this point is actually 1. So those would be our limits of integration. And then we're just going to set up 1/4 plus sine of pi times x plus 1. That's big R squared minus, and then we're going to have to set up 4 to the negative x plus 1 squared. That's little r squared, and then we have dx. Okay, so this would be our definite integral that would find the volume of revolution. Okay. Next application is solving differential equations by separating the variables. Okay, so you guys, you'll recognize these because you'll see like the dx over dt or the dy over dx in the problem. And so this is where you want to separate your variables. So we want x and dx on one side, and then we want e to the negative t and dt on the other side, okay? So I'm noticing here that we could multiply by the dt on each side, and initially it would look like this, because we're going to have 1 times dt, which is dt. Okay, so we've gotten a little bit closer. Now what we could do is divide by the e to the negative t on each side, and then we'll have x times dx equals, and then I'd probably flip this and just make it e to the t times dt. So this is what I mean by separating the variables. After you do that, you're ready to integrate both sides. So the antiderivative of x is x squared over 2. And I'm going to add my plus c on this side, because this is an indefinite integral. And then the antiderivative of e to the t is just e to the t. Okay, now, I want to go back to my initial condition here, because this is going to help us solve for c. This is x of 0 equals 1. So this is like x of t, okay? So t is equal to 0 and x of t is equal to 1. So we're actually going to solve this for x. So because of that, I'm actually going to put my plus c on the other side. Okay, so we want to solve this for x. So we would multiply by 2 on both sides. And then we would square root both sides. Okay, now remember, technically we get 2 solutions, positive and negative. But again, because of our initial condition here, x of 0 equals positive 1, I know I'm looking for the positive root. Okay, so x will equal the square root of 2 times e to the t plus c. Okay, then we can use our initial condition. So remember, that was x of 0 equals 1. We're going to plug in 1 for x and 0 for t. Okay, now remember, e to the 0 is equal to 1. So this just ends up equaling the square root of 2 plus c. And then to solve for c, we would square both sides, subtract 2, and we'll get negative 1 is equal to c. And then we'll just plug that in. And voila, we have solved the differential equation. Okay, now, some differential equations cannot be solved algebraically. So in that case, we try to take a graphical approach, which is called a slope field. So remember that the differential equation represents the derivative, and the derivative is slope. Slope at a point. So when you're given a problem like this, and you're asked to sketch a slope field, all you're doing is finding the slope at each point and then drawing a little tangent line with that slope, okay? So our differential equation is x squared times y minus 1. My suggestion would be to set up a table of values to try to find all of these slopes. And we're asked to do this at 12 different points. So our ordered pairs would be, and I'm just going to start at this point here. So that would be negative 1, 3, and we'd have negative 1, 2, negative 1, 1, and negative 1, 0. Okay, and then we have 0, 3, 0, 2, 0, 1, 0, 0. And then we have 1, 3, 1, 2, 1, 1, 1, 0. Okay, so we're just taking these values and plugging them in. So I'm just going to shorten this video, pause it, fill that out, and then I'll come back. Okay, so I have taken all of our ordered pairs and plugged them into x squared times y minus 1, and I came up with all these slopes. Okay, so now we're just going to sketch a small tangent line with each slope, okay? All right, so at negative 1, 3, the tangent line has a slope of 2. So we want to make that, steep, but with a positive slope. And then at negative 1, 2, there's a slope of 1. Negative 1, 1, the slope is 0, so that's a horizontal tangent line. And then at negative 1, 0, we have a slope of negative 1. Okay, then all of these were pretty easy because you end up with 0 as your slope. And then at 1, 3, again, we have a slope of 2, then a slope of 1, then a slope of 0, and then a slope of negative 1. And that would be our slope field. Okay, now sometimes instead of being asked to draw a slope field, you might have to match them. In this example, we're matching it to the differential equation. So I just wanted to remind you that when you're looking at the slope field, if your tangent lines are the same horizontally, so like if you look at slope field for B, if you look, excuse me, these are vertically the same. Let's look at D. These are horizontally the same. If you look at your slope fields horizontally, they're the same. So that is kind of a hint that your okay, sorry, I had a short interruption. But anyway, when you're looking at your slope field, like in D, if you notice your tangent lines are the same horizontally. So that means that you're looking for a differential equation in terms of y, because for that same y value, you're getting the same tangent line or the same slope of the tangent line. So D would actually match with this differential equation. And then if you look back to B, here the tangent lines are the same vertically. So it's kind of saying like for that one value of x, we're getting the same slope. So you're looking for an equation that is only in terms of x. So that would match with this equation. And then to match up the other two, I would just pick a point and see if it works. Like for A, we could pick 0, 1 and see if it works. So if x is 0 here, we'll get 0 minus 1. Well, that would equal negative 1, but this tangent line has a slope of 0 because it's horizontal. So let's see if it works down here. Here we'd end up with negative 0 over 1, and that would equal 0. So it certainly looks like this one matches up with A, and then this one would have to match up with C. Okay? All right, and then our last application is exponential growth and decay. So remember, anytime you read something like this, let y be a function of time t, the rate of change of y is directly proportional to y. So remember, in that case, we're saying that dy over dt is equal to k times y. And if we solve that using separation of variables, I'm not going to take you all the way through that, you end up with an exponential function y equals c times e to the kt. All right, here's an example. The new themed restaurant in town called Rowdy Rita's Eat and Hurl is being tested by the health department for cleanliness. Health inspectors find the men's room floor to be a fertile ground for growing bacteria. They have determined that the rate of bacterial growth is proportional to the number of colonies. There's the key phrase. So we know we're dealing with y equals c times e to the kt. So they plant 10 colonies. C is your initial amount, so C is equal to 10. And come back 15 minutes later. When they return, the number of colonies has risen to 35. Okay, this gives us an ordered pair. After 15 minutes, there are 35 bacteria in the colony. How many colonies will there be 1 full hour after they planted the original 10? Okay, so what we need to do here is we need to use what we were given and solve for K. We have to find that rate. So we're going to plug in 35 for Y, 10 for C, 15 for T. We're going to solve this for K. So we're going to divide by 10. We're solving an exponential equation, so we're going to take the natural log of each side. Those will cancel out. And then we're going to divide by 15. And then if you plug this in the calculator, K is approximately 0.08352. Okay, so now we have our equation, or function. Y is equal to, remember, C is 10, times e to the 0.08352 times t. And now we can use that equation to answer the question, how many colonies will there be 1 full hour after they planted the original 10? We're going to plug in 60 minutes for t, because that's 1 full hour. And again, you're just going to key that in your calculator. And we end up with approximately 1,500 bacteria. Okay. All right, you guys. So that should wrap up your note cards. So please take some time to, watch any videos you haven't or review any that you need to. Study those note cards, and we will start our mock exam on Monday. All right. Have a good weekend.